A few months ago, the Nobel Prize in Physics was awarded to two teams of astronomers and other distant galaxies. We may find that our universe is not the only universe, but is instead part of a vast complex of universes, everything. And I say most of us with forethought, as my 4-year-old daughter has heard me speak of these ideas since she was born. And last year, I was holding her and I said, "Sophia, I love you more than anything in the universe." And she turned to me and said, "Daddy," as it just might be right. I'm going to tell the story of the multiverse in 3 parts. In part 1, I'm going to describe those Nobel Prize-winning results and highlight a profound mystery, which part 3, I'm going to describe a cosmological theory called inflation, which will pull all the pieces of the story together. Okay, part 1 starts back in 1929. There was one thing that everyone was certain of. The expansion must be slowing down. That is, much as the gravitational pull of the Earth slows the ascent of an apple tossed upward, the gravitational pull of each galaxy on every other must be slowing the expansion of space. The expansion has been slowing. And they did this by painstaking observations of numerous distant galaxies, allowing them to chart how the expansion rate has changed over time. Here's the surprise. They found that the expansion is not slowing down. Instead, they found that it's speeding up, going faster. That you'd want to know why. What's pushing on it? Similarly, the astronomers' results are surely well deserving of the Nobel Prize, but they raised an analogous question. What force is driving all galaxies to rush away from every other at an ever-quickening speed? Well, the most promising answer, together. But in Einstein's theory of gravity, his general theory of relativity, gravity can also push things apart. How? Well, according to Einstein's math, if space is uniformly filled with an invisible energy, sort of like a uniform invisible mist, then the gravity generated by that mist would be repulsive. Repulsive gravity, which is just made it smoky white here so you can see it. Its repulsive gravity would cause each galaxy to push against every other, driving the expansion to speed up, not slow down. And this explanation represents great progress. But to account for the cosmic speed up, look at what they found. This number is small. Expressed in the relevant units, it is spectacularly small. And the mystery is to explain this peculiar number. We want this number to emerge from the laws of physics, an idea that naturally emerges from string theory, which takes me to part 2, string theory. So hold the mystery. I now go on to tell you 3 key things about string theory. First off, what is it? Well, it's an approach to realize Einstein's dream of a unified theory of physics, a single overarching framework that would be able to describe all the forces at work in the universe. And the central idea of string theory is quite straightforward. It says that if you examine any piece of matter ever more finely, at first you'll find molecules, and then you'll find atoms and subatomic particles. But the theory says that if you could probe smaller, much smaller than we can with existing technology, you'd find something else inside these particles. A little tiny vibrating filament of energy, a little tiny vibrating string. And just like the strings on a violin, they can vibrate in different patterns, producing different musical notes. These little fundamental strings, when they vibrate in different patterns, they produce different kinds of particles. So electrons, quarks, neutrinos, photons, all other particles would be united into a single, would all arise from vibrating strings. It's a compelling picture, a kind of cosmic symphony where all the richness, that height, width, and depth. But string theory says that on fantastically small scales, there are additional dimensions crumpled to a tiny size, so small that we have not detected them. But even though the dimensions are hidden, they would have an impact on strings, can vibrate. And in string theory, vibration determines everything. So particle masses, the strengths of forces, and most importantly, the amount of dark energy of the extra dimensions, we should be able to calculate these features, calculate the amount of dark energy. The challenge is we don't have 5 different candidate shapes, so you can imagine analyzing them one by one to determine if any yield the physical features we observe. But over time, the list grew as researchers found other candidate shapes. From 5, the number grew into the hundreds and then the thousands. A large but still manageable collection to analyze, since, after all, graduate students need something to do. But then the list continued to grow into the millions and the billions until today. The list of candidate shapes has soared to about 10 to the 500. These shapes is on an equal footing with every other. Each is as real as every other in the sense that there are many universes, each with a different shape for the extra dimensions. And this radical proposal has a profound impact on this mystery, the amount of dark energy revealed by the Nobel Prize winning results, because you see, if there are other universes, and if those universes each have, say, a different shape for the extra dimensions, then the physical features of each universe will history of explaining the amount of dark energy we've now measured would take on a wholly different character. In this context, there are many numbers, which means we have been asking the wrong question. Instead, the right question to ask is, why do we humans find ourselves in a universe with a particular make headway? Because those universes that have much more dark energy than ours, whenever matter sees the repulsive push of the dark energy is so strong that it blows, and galaxies don't form. And without galaxies, there are no stars, no planets, and no chance for our form of life in a universe with the particular amount of dark energy we've measured, simply because our universe has conditions hospitable to our form of life. And that would be that. Mystery solved, multiverse found. Now, some find this explanation unsatisfying. We're used to physics giving us definitive explanations for the features we observe. But the point is, if the feature you're observing can and does take on a wide variety of different values across the wider landscape of reality, then seeking one explanation for a particular value is simply misguided. An early example comes from the great astronomer Johannes Kepler, who was obsessed with understanding a different number, why the sun is 93 million distances from their host star, so hoping that the laws of physics will explain one particular number, 93 million miles. Well, that is simply wrong-headed. Instead, the right question to ask is, why do we humans find ourselves on a planet at this particular distance instead of any of the other possibilities? And again, that's a question we can answer. Those planets which are much closer to a star like the sun would be so hot that our form of life wouldn't exist. And those planets that are much farther away from the star, well, they're so cold that, again, our form of life would not take hold. So we find ourselves on a planet at this particular distance simply because of other universes. And that takes me to my final part 3, because such a mechanism has been found by cosmologists trying to understand the Big Bang. You see, when we speak of the Big Bang, we often have an image of a kind of cosmic explosion that created our universe and set space rushing outward. But there's a little secret. The Big Bang leaves out something pretty important: the bang. It tells us how the universe evolved after the bang, but gives us no insight into what would have powered the bang itself. And this gap was finally filled by an enhanced version of the Big Bang theory. It's called inflationary cosmology, which Big Bang, but it would also generate countless other Big Bangs, each giving rise to its own separate universe, with our universe and now, if we meld this with string theory, here's the picture we're led to. Each of these universes has extra dimensions. We find ourselves in one universe instead of another, simply because it's only in our universe that the physical features, like the amount of dark energy, are right for our form of life to take hold. And this is the compelling but highly controversial picture of the wider cosmos that cutting-edge observation and theory has now lit. Well, let me describe one way that might one day happen. The inflationary theory already has strong observational support because the theory predicts that the Big Bang would have been so intense that as space rapidly expanded, tiny quantum jitters from the micro world would have been stretched out to the macro world, yielding a distinctive fingerprint, a pattern of slightly hotter spots and slightly colder spots across space. That collision would generate an additional subtle pattern of temperature variation to detect. And so exotic as this picture is, it may one day be grounded in observations establishing the existence of other universes. That expansion is speeding up. In the very far future, rush away so far and so fast, not because of technological limitations, but because of the laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. To be wrong. Now, maybe those future astronomers will have records handed down from an earlier era, like ours, attesting to an expanding cosmos teeming with galaxies. But would those future astronomers believe such ancient knowledge? Or would they believe in the black, static, empty universe that their own state-of-the-art observations reveal? I suspect the latter, which means that we are living through a remarkably privileged era when certain deep truths about the cosmos are still within reach of the human spirit of exploration. It appears that it may not always be that way, because today's astronomers, by turning powerful telescopes to the sky, have captured a handful of starkly informative photons, a kind of cosmic telegram, billions of years in transit, and the message echoing across the ages is clear. Sometimes nature guards her secret.
Brian, thank you. The range of ideas you've just spoken about are dizzying, exhilarating, incredible. How do you think of where cosmology is now in a sort of historical side? Are we in the middle of something unusual historically, in your opinion?
Well, it's hard to say. When we learn that astronomers of the far future may not have enough information to figure things out, the natural question is, maybe we're already in that position. The data from the microwave background radiation that was set down 13.72 billion years ago, and yet we can do calculations today to predict how it will look, and it matches. Holy cow, that's...
2 days. Maybe some of these conversations can continue. Thank you.
My pleasure.
So much. Thank you, Brian.
Like Idle Time Books and Panther Coffee, with free enterprise puns like Hue and Cry and Smash Records. And one Saturday a year, small businesses remind a nation of the benefits of shopping small to bliss with every bride-to-be.
Absolutely stunning.
On just one day, 100 million of us joined a movement. And Main Street found its might again. And Main Street found its fight again. And we, the locals, found delight again.
That's the power of all of us.
That's the power of all of us.
That's the power of all of us.